Electromagnetic radiation consists of wavelengths that carry electromagnetic radiant energy. These wavelengths help describe various types of light, such as radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Radio waves have the longest wavelengths, while gamma rays have the shortest wavelengths. There are different types of radiation that can cause different types of transitions. Microwave radiation includes transitions of molecular rotational levels. Infrared waves causes transitions in molecular vibrational levels. And finally, ultraviolet and light rays cause transitions in electronic energy levels. Colorimetry is essentially the measurements of the wavelengths and intensity of electromagnetic radiation when the light rays are visible. We use colorimetry to identify substances and measure the concentration of those substances that absorb light. When using cuvettes and colorimetry, you cannot leave fingerprints because it will cause inaccuracies in the measurements. The absorbance would appear higher than it actually is, since less light will be emitted through the cuvette. You cannot use colorimetry to determine the concentrations of clear substances like water and sodium chloride. They are both clear solutions, so the absorbance would be zero no matter what the different concentrations are. Beer-Lambert law is a law that is applied to the act of determining the concentrations of substances that absorb light. It states that there is a linear relationship, proportional, between concentration and the absorbance of a solution. It allows the concentration of a solution to be calculated by measuring absorbance. Basically, a more concentrated solution absorbs more light compared to a diluted solution.
The ground state of an atom is the lowest energy state of that atom. When those atoms are given energy to be absorbed, they move to a higher energy level. When those electrons within the atom have reached the highest energy level, the atom is now in an excited state, which is not a very stable state for it to be in. When it returns back to the ground state, it releases energy in the form of photonic light, otherwise known as electromagnetic radiation. The larger the difference between the two energy levels that the electrons occupy as they make that journey will dictate the color that is emitted during the transition back from the excited state to the ground state. So for example, if an electron moves from, say, electron shell 2 to electron shell 6, that's a large transition. So when it goes from that excited state back to that ground state, it's releasing energy in the form of photons with a very small wavelength and a high frequency. And along with this, we can use emission spectroscopy to examine the wavelengths of photons emitted as the atom, or the electrons within the atom, transition from that highest energy level to the lowest energy level. And next up, we have these two main equations that we use when determining the wavelength, frequency, or energy of a given situation. So the first equation is E equals h, otherwise known as Planck's constant, times v, otherwise known as frequency. And then the second equation is c, which is the speed of light, equals wavelength times v, which is frequency. When determining the energy of a given situation, the unit will always be in joules. And when determining the frequency, the unit will always be in hertz, or s to the -1. Wavelength is typically in nanometers. Planck's constant, which is incorporated into the E equals hv equation, is 6.626 times 10 to the -34th power, and the speed of light, which is incorporated in the C equals wavelength times frequency equation, is 2.998 times 10 to the 8th power. I hope this information was helpful, and thank you for listening.